long before there was a sunrise, long before there were oceans, mountains, moons, or planets, long before the first gentle light of morning ever touched the surface of Earth, there was only darkness, dust, and time. Not empty darkness, not nothing, but a vast cold cloud drifting through the Milky Way. It was made of hydrogen and helium, the simplest elements in the universe. But mixed within it were tiny grains of heavier material, little fragments of carbon, silicon, iron, oxygen, magnesium, and ice. These were the ashes of ancient stars. Long before our sun existed, other stars had already lived and died. Some had burned quietly for billions of years. Some had exploded violently, scattering their enriched material into space. And so, in the darkness before the solar system, the ingredients were already waiting. The atoms that would one day become Earth were there. The iron that would sink into Earth's core was there. The oxygen that would help make water was there. The carbon that would one day become part of living things was there. Even the calcium in bones, the silicon in rocks, and the metals inside future planets were present as dust and gas, drifting in a great interstellar cloud. This is where the story begins. Not with the sun, not with Earth, but with the remains of older stars floating silently between the spiral arms of the galaxy. For a long time, the cloud may have seemed almost still. Enormous, cold, and faint, it moved through the Milky Way like mist across a dark valley. Within it, tiny motions stirred. Particles drifted, turbulence curled, magnetic fields threaded through the gas. Nearby stars shone and died. Perhaps a shock wave from a distant supernova passed through part of the cloud. Perhaps the slow pressure of galactic motion disturbed it. The exact trigger is still studied, but somehow, in one region of that ancient cloud, balance was lost. Gravity began to win. At first, the collapse was gentle. A little gathering, a little thickening, a slight deepening of density in the cold. But gravity has patience. The more material gathered, the stronger its pull became. The stronger its pull became, the more material it gathered. Slowly, the cloud began to fall inward upon itself. It was the beginning of a star. As the cloud collapsed, it did not simply fall straight down into one point. It had a little rotation. Almost everything in space does. Even the most delicate cloud has some twist, some inherited motion, some faint turning from the long history of the galaxy. And as the cloud shrank, that small rotation became more important. Like a skater drawing in their arms and spinning faster, the contracting cloud began to rotate more quickly. The material falling inward flattened into a disk around the growing center, a disk of gas and dust, wide, thin, turning. At the heart of it, matter gathered into a dense young object, a protostar. Around it, the remaining material spread outward in a glowing, dusty, turbulent ring. This was the solar nebula, the nursery of the sun, the cradle of planets. The solar system was not yet a system. It was a storm, a flat, rotating storm of dust and gas surrounding a newborn star. There was no Mercury, no Venus, no Earth, no Mars, no Jupiter with its bands, no Saturn with its rings, no icy moons, no comets, no blue planet. Only a young sun forming in the center, and around it a vast disk of possibility. In the center, pressure grew. The protosun became hotter and denser as gravity pulled more material inward. At first, it shone not by nuclear fusion, but by heat from collapse. Matter fell, compressed, and warmed. The young sun glowed with the energy of its own formation. Around it, the disk spun. Near the center, temperatures were high. Dust grains were baked. Ice could not survive. Only metals and rocky minerals could remain solid. Farther out, the disk was cooler. Water ice, methane ice, ammonia ice, and other frozen compounds could exist. Beyond a certain region, often called the frost line or snow line, there was more solid material available, because ice could join rock and metal in the building of worlds. This simple temperature difference would help shape the architecture of the solar system. Close to the Sun, small rocky planets would form. Farther out, giant worlds could grow. And even farther away, icy bodies would remain as relics of the beginning. But in those first ages, none of this had yet happened. The disk was alive with motion. Tiny grains of dust circled the young sun. Some were smaller than smoke particles. Some were crystals of minerals that had condensed from hot gas. Some were inherited grains from ancient stars, older than the solar system itself. They orbited together in streams and eddies, colliding gently, clinging by static forces, sticking, separating, and sticking again. A planet begins humbly, not as a sphere, not as a world, but as dust. A grain touches another grain. A cluster forms. A fragile flake becomes a pebble. Pebbles gather into larger pieces. The process is not perfect. Many collisions destroy as much as they build. Some fragments bounce, some shatter, some spiral inward toward the sun. Some are carried by gas currents. But across millions of years, in a disk wide enough to contain every future planet, the small becomes large. Dust becomes pebbles. Pebbles become stones. Stones become boulders. Boulders become planetesimals. Planetesimals are the first true building blocks of planets. They may be kilometers across, large enough for gravity to matter more strongly. They pull on nearby material. They collide with other bodies. Some merge, some break. Some become seeds around which larger worlds grow. The young solar system was not quiet. It was full of impacts. Not explosions in air because there was no air, but silent collisions in space. Rock struck rock, metal struck stone, ice struck dust, bodies shattered, reformed, and collided again. Every growing world was both builder and battlefield. In the inner solar system, where heat from the young sun drove away most ice and gas, the material was mostly rock and metal. Here, the future terrestrial planets began to take shape. Mercury, closest to the Sun, formed in the hottest region. It would become small and dense, with a large iron core. Its history is still debated, but perhaps early impacts stripped away some of its outer rocky layers, or perhaps it formed from material naturally rich in metal. Today, Mercury is a scarred world, airless and extreme, turning slowly under intense sunlight. Venus formed farther out, near Earth's region. It was roughly Earth-sized, made of rock and metal, with enough gravity to hold an atmosphere. In its early days, Venus may have been very different from the world we see now. Today, it is wrapped in thick carbon dioxide clouds, with crushing pressure and surface heat strong enough to melt lead. But in the story of formation, Venus was one of the rocky siblings, born from the same inner disk, Earth formed nearby. At first, it was not blue, it was not gentle, it was a molten, growing planet, struck again and again by smaller bodies. Each impact delivered energy. Each collision heated the young Earth. Radioactive elements inside it added more warmth. Metal sank downward, forming the core. Lighter rock rose outward, forming mantle and crust. The planet separated into layers, like a fruit forming skin around a dense inner seed. Mars formed beyond Earth, smaller and colder. It too was built from rocky material. It may have grown quickly, but never became as large as Earth or Venus. Its lower gravity would shape its future. Mars would cool faster. Its inner heat would fade sooner. Its atmosphere would become thin. But in the beginning, it too was a young world in the making. Between Mars and Jupiter, there was material enough for many bodies, but not for a full planet. Jupiter's gravity disturbed this region, stirring orbits and increasing collision speeds. Instead of gently assembling into one large planet, much of the material remained scattered. Over time, it became the asteroid belt, a region of rocky leftovers, fragments, and small worlds, including Ceres, Vesta, Pallas, and countless smaller bodies. The asteroid belt is not the crowded field of stones sometimes imagined. It is vast. mostly empty. A spacecraft can pass through it without weaving between rocks. But in cosmic terms, it is rich with memory. Asteroids are among the preserved leftovers of planet formation. Some have been altered by heat and impacts. Others remain primitive, holding clues to the earliest solid materials that orbited the young sun. Beyond the frost line, the story changed. There, ice joined rock and metal. There was more solid material. Larger planetary cores could grow. And once a core became massive enough, it could begin pulling in gas from the surrounding disk. Jupiter was the great first giant. It formed from a massive core, or through rapid disk instability, or perhaps through a process involving both ideas. Scientists continue to study the details. But somehow, early in the solar system's history, Jupiter gathered enough material to become immense. It drew in hydrogen and helium, the same light gases that filled the sun, and wrapped itself in a vast atmosphere. Jupiter became the largest planet, a world more massive than all the other planets combined. Not a star, because it never gained enough mass to ignite sustained hydrogen fusion in its core, but still a giant presence. Its gravity shaped everything around it. It stirred the asteroid belt. It influenced the formation of Mars. It pulled comets and asteroids into new paths. It became, in many ways, the architect of the solar system's middle regions. Around Jupiter, a smaller disk formed. A disk around a planet. In that circumplanetary disk, moons were born. The four great Galilean moons, Io, Europa, Ganymede, and Callisto, likely formed in orbit around Jupiter from material circling the young planet. They are like a miniature solar system, worlds arranged around a giant, each with its own nature. Io, closest of the four large moons, became a world of volcanoes. Its interior is squeezed and flexed by Jupiter's gravity and by the pull of neighboring moons, creating intense tidal heating. Today, Io is the most volcanically active body known in the solar system. Europa, smooth and icy, hides one of the great mysteries of the solar system. Beneath its frozen crust may lie a global ocean warmed by tidal energy. It is not the largest moon, not the brightest in the sky, but it may be one of the most intriguing places in the search for environments where life could exist. Ganymede became the largest moon in the solar system, bigger than Mercury. It has its own magnetic field, an icy surface, and perhaps hidden layers of water deep below. Callisto, ancient and heavily cratered, preserved the memory of early bombardment. Its surface is one of the oldest in the solar system, a record of impacts from the deep past. These moons did not simply appear. They were born from the same broad process that made planets: disk, dust, ice, gravity, collisions, and time. Saturn formed farther out. Like Jupiter, it gathered hydrogen and helium, becoming a gas giant. It is less massive than Jupiter, but vast and graceful, wrapped in bands of cloud and encircled by the most spectacular ring system in the solar system. Saturn's rings are made mostly of ice particles, from grains to boulders, all orbiting in a thin, shining disk. Their origin is still debated. They may be ancient, or they may be much younger than Saturn itself, perhaps formed when an icy moon was shattered by tidal forces or collision. Whatever their age, they are not permanent in the deepest sense. Rings evolve, particles collide, material spreads. Some falls inward. Even beauty in space has a lifetime. Around Saturn, moons formed and gathered. Titan became the largest of them, a moon bigger than Mercury, wrapped in a thick nitrogen atmosphere. On Titan, methane and ethane fall as rain, carve rivers and fill lakes and seas. It is a moon that behaves almost like a planet, with weather, clouds, and landscape shaped by liquids, though not liquid water on the surface. Enceladus, much smaller, hides another wonder. Its icy crust covers a subsurface ocean, and from cracks near its south pole, plumes of water vapor and ice spray into space. In those plumes are hints of chemistry from the ocean below. Like Europa, Enceladus is a reminder that worlds do not need to be large, warm, or close to the Sun to be geologically alive. Uranus and Neptune form still farther out in colder regions of the disk. They are often called ice giants, not because they are solid balls of ice, but because they contain large amounts of heavier, volatile materials compared with Jupiter and Saturn. Water, ammonia, methane, and other compounds helped shape them. They also have hydrogen and helium atmospheres, but they are different from the gas giants. Uranus is tilted dramatically, spinning almost on its side. Perhaps a huge impact early in its history knocked it over. Its moons and rings follow its strange orientation, making the whole system seem like a tilted clock turning through the dark. Neptune, farther still, is a world of fierce winds and deep blue color, shaped partly by methane in its atmosphere. Its largest moon, Triton, is especially strange. Triton orbits Neptune backward compared with the planet's rotation, a strong clue that it did not form there in the usual way. It was likely captured, perhaps once a Kuiper Belt object drawn into Neptune's gravity and transformed into a moon. Capture is another way moons can come to be. Not every moon is born from a disk around its planet. Some form from giant impacts. Some are captured wanderers. Some may be fragments. Some may be rubble piles held together by gravity. The solar system is not one story repeated exactly. It is many stories, all shaped by gravity and time. Earth's moon is the most familiar example of a moon born from violence. The leading idea is the giant impact hypothesis. Early in Earth's history, when the planet was still hot and growing, a Mars-sized body, often called Theia, struck the young Earth. The collision was enormous. Material from Earth and the impactor was blasted into orbit. This debris formed a disk around Earth, and from that disk, the moon gathered. The exact details are still being refined. Scientists study lunar rocks, isotopes, computer models, and the chemistry of Earth and Moon to understand what happened. But the broad picture remains powerful. Our moon was likely born from a catastrophic impact. At first, the moon was much closer to Earth than it is today. It would have appeared enormous in the sky. Both Earth and Moon were hot. The moon's surface may have been covered by a magma ocean. As it cooled, lighter minerals floated upward, forming an early crust. Later impacts scarred the surface, creating basins. Lava filled some of them, making the dark Luna Maria we see from Earth today. The moon has been moving slowly away from Earth ever since, because of tidal interactions. Each year, it drifts a little farther. In return, Earth's rotation gradually slows. The dance between Earth and Moon is not fixed. It evolves. And this moon, born from impact, would shape Earth profoundly. It stabilizes Earth's axial tilt, helping moderate long-term climate variations. It raises tides in the oceans. It slows Earth's spin across geological time. It lights the night. It records impacts from the early solar system on a surface that does not have wind, rain, oceans, or plate tectonics to erase them quickly. The moon is not just a companion, it is a witness, a preserved archive of the early violence that shaped the inner solar system. Mars has two small moons, Phobos and Deimos. They are irregular, dark, and asteroid-like. For a long time, many suspected they were captured asteroids. But their nearly circular, equatorial orbits complicate the story, and other formation ideas involve debris from an impact around Mars. Their origin remains uncertain. Like many small moons, they carry questions rather than simple answers. The giant planets have many small, irregular moons, often distant, tilted, and eccentric in their orbits. Many were likely captured from passing populations of small bodies. These moons are remnants of ancient encounters, gravitational accidents preserved over billions of years. Moons reveal the solar system's creativity. They can be volcanic like Io, ocean-bearing like Europa and Enceladus, atmospheric like Titan. captured like Triton, impact-borne like Earth's moon, dark and irregular like many small outer moons. Some are larger than planets. Some are barely held together. Some are geologically dead. Some may be active beneath ice. Around every planet, the story of formation continued in different forms. But while planets and moons were growing, the young sun itself was changing. At the center of the disk, the protosun became hot and dense enough for nuclear fusion to begin. Hydrogen nuclei began to fuse into helium. Energy emerged from the core. The sun became a true star. A star's birth is not an instant like a lamp switching on, but once fusion stabilized, the sun entered the long main stage of its life. Radiation streamed outward. A solar wind blew through the remaining disk, pushing away gas and fine dust. The era of planet building began to end. The gas disk did not last forever. This mattered deeply. The giant planets had to gather their enormous atmospheres while gas was still available. Once the young sun cleared the disk, the chance to become a gas giant was largely over. Worlds that had not become large enough by then remained rocky, icy, or small. Timing shaped destiny. Jupiter and Saturn grew early enough to become giants. Uranus and Neptune grew in colder outer regions, perhaps more slowly, with less gas available. The inner planets formed where gas could not easily remain and where heat kept volatile materials scarce. Asteroids remained where Jupiter stirred growth into incompletion. Kuiper belt bodies remained beyond Neptune, where ice and rock preserved early conditions. The solar system was becoming a family, but it was not yet calm. Young planets do not form in neat, peaceful orbits from the beginning. They jostle, they migrate, they scatter smaller bodies, they pull on one another. The giant planets especially may have shifted positions after they formed. Models of planetary migration suggest that Jupiter, Saturn, Uranus, and Neptune did not necessarily form exactly where we see them now. Jupiter may have moved inward and then outward in the early disk, affecting the amount of material available to Mars and reshaping the asteroid belt. Later, the outer planets may have migrated, with Neptune moving outward and disturbing the Kuiper belt. These ideas are still refined and debated, but they help explain why the solar system looks the way it does. The solar system is not a clock assembled once and left unchanged. It is an evolving landscape. In the outer regions, Neptune's migration likely scattered icy bodies. Some remained in the Kuiper belt, a broad, donut-shaped region beyond Neptune. Some were pushed into resonant orbits. Pluto, for example, follows an orbit linked to Neptune in a stable pattern. For every 3 times Neptune orbits the Sun, Pluto orbits twice. Pluto is not alone. It is one of many icy worlds in the outer solar system. There are dwarf planets such as Eris, Haumea, Makemake, and others. There are smaller Kuiper belt objects, icy fragments, binaries, and ancient bodies that preserve clues to the early disk. The Kuiper belt is like a cold attic of the solar system, holding objects left over from construction. Beyond the Kuiper belt lies a realm much more distant and less directly observed, the Oort cloud. It is thought to be a vast spherical cloud of icy bodies surrounding the solar system at enormous distances. These objects may have been scattered outward by the giant planets early in solar system history, then gently influenced by passing stars and the gravity of the galaxy. Long-period comets may come from this distant cloud. They fall inward from the cold, carrying ancient ice toward the sun. As they approach, sunlight warms them. Frozen gases vaporize. Dust lifts away. A coma forms around the nucleus, and tails stretch out through space, always shaped by sunlight and the solar wind. Comets are among the most beautiful leftovers of formation. They are not omens in the old sense. They are archives. Dirty snowballs, icy dirt balls, fragile mixtures of frozen gases, dust, rock, and organic molecules. Some may preserve material from the earliest solar nebula. Some may have delivered water and carbon-rich chemistry to the young Earth, though the exact sources of Earth's water likely involved a mixture of contributions, including water-bearing asteroids and perhaps some comets. The early Earth needed water. Today, oceans cover most of its surface. But during formation, the inner solar system was hot, and the young Earth endured violent impacts and periods of melting. Where did its water come from? Some water may have been incorporated into the building blocks of Earth from the beginning, locked inside minerals and materials that formed not completely dry. More may have arrived later from water-rich asteroids, especially from the outer part of the asteroid belt. Comets may have contributed some water, but measurements of water isotopes show that not all comets match Earth's oceans. The full story is complex. What matters for the narration of the solar system is that Earth's water is ancient. It has passed through rock, vapor, ice, impact, ocean, cloud, and rain. Some of the water in a sleeping body tonight may contain atoms that were once part of interstellar ice, once trapped inside small planetary building blocks, once delivered through the violence of formation, once held in steam above a molten Earth. Nothing about a calm ocean is simple when traced backward. Every wave has a cosmic ancestry. After the planets formed, the solar system entered a long period of clearing. Many leftover planetesimals remained. Some collided with planets and moons. Some were ejected from the solar system. Some were thrown inward toward the sun. Some were trapped in belts and resonances. Some became moons. Some became comets. Some survived as asteroids. The early bombardment shaped surfaces everywhere. Mercury was cratered. The Moon was cratered. Mars was cratered. The icy moons were struck. Even Earth was struck, though Earth's active geology later erased much of the visible record. There may have been a period of especially intense impacts, several 100 million years after formation, sometimes called the Late Heavy Bombardment. Though its exact timing, intensity, and even whether it was a sharp spike or a longer decline are still debated. The Moon preserves evidence of ancient basins, but interpreting the record is difficult. Still, the young solar system was certainly more crowded than it is today. Space near the planets was not empty. It contained debris, fragments, and wandering bodies. Slowly, over hundreds of millions of years, the chaos faded. The planets cleared their neighborhoods, orbits stabilized. The sun settled into its long life. The small leftover bodies found their reservoirs: asteroid belt, Trojan groups, Kuiper belt, scattered disk, Oort cloud. The system became quieter, not perfectly quiet, but quieter. And from this quiet, Earth became habitable. At first, Earth was hot and hostile. The surface melted and remelted. Heavy bombardment shook the crust. Volcanoes released gases. Steam filled the atmosphere. As the planet cooled, liquid water could remain on the surface. Oceans gathered, rocks weathered, the atmosphere evolved, the Moon pulled tides across the young seas. Somewhere, through chemistry still under study, life began. The solar system, born from dust, had produced at least one world where dust became alive. This is perhaps the most extraordinary transformation in the entire story. A molecular cloud collapses, a star ignites, planets form, moons gather, comets deliver ice, a rocky planet cools. Water flows, chemistry deepens, and eventually, life opens its eyes beneath a star made from the same cloud. But to tell the story well, we must return to the beginning again, because the formation of the solar system is not a straight line, it is a weaving of scales. The smallest dust grains matter. The largest planet matters. The young sun matters. The position of the frost line matters. The timing of gas dispersal matters. The migration of giant planets matters. The chance of collisions matters. The capture of moons matters. The survival of leftover bodies matters. A solar system is not made by one event. It is made by many. Gravity gathers, heat separates, Collisions build, radiation clears, tides warm, impacts destroy and create, migration rearranges, time preserves and erases. The planets we know are the survivors of this process. Mercury survived close to the Sun, dense and scarred. Venus survived as Earth's near twin in size but not in climate. Earth survived with water, a large moon, plate tectonics, atmosphere and life. Mars survived as a smaller world, once more active, now cold and dry on the surface. Jupiter survived as the giant, keeper of storms and moons. Saturn survived as the ringed world, pale and immense. Uranus survived tilted, quiet and strange. Neptune survived at the edge, blue and windy, guardian of the outer darkness. And around them move moons, each a chapter. The moon, born from impact. Phobos and Deimos, uncertain and small. Io squeezed into fire. Europa, ice over ocean. Ganymede, large enough to feel almost planetary. Callisto, old and cratered. Titan, orange and atmospheric. Enceladus, venting ocean into space. Mimas, Tethys, Dione, Rhea, Iapetus and many others. Miranda, Ariel, Umbriel, Titania, Oberon around Uranus. Triton around Neptune, captured and cold, with geysers of nitrogen seen by Voyager 2. Small moons shepherd rings. Irregular moons travel on distant tilted paths. Some moons may be temporary, some may be doomed. Phobos is slowly spiraling inward toward Mars and may eventually break apart or crash. Triton's capture may have destroyed earlier Neptunian moons. Saturn's rings may one day darken and disperse. The solar system still changes, very slowly. But it changes. Even today, comets fall inward. Asteroids occasionally strike planets. Dust spirals toward the sun. The solar wind streams outward. The moon recedes from Earth. The sun gradually brightens over its main sequence lifetime. Nothing is perfectly still. The birth of the solar system ended long ago, but its evolution continues. There is a calmness in seeing the solar system as a natural habitat. Not merely a list of planets, but an ecosystem of gravity. The sun is the central source of light and heat. The planets are great environments shaped by distance, composition, size, and history. Moons are smaller worlds, some more active than planets. Asteroids and comets are the remnants, the seeds that never became worlds, the fragments that remember the beginning. The solar wind flows through it all like weather from a star. Magnetic fields form invisible shields and tails. Radiation belts surround giant planets. Dust rings and resonances mark hidden gravitational patterns. Everything is connected. Jupiter's gravity affects asteroids. Saturn's moons sculpt rings. Neptune shapes the Kuiper belt. The moon shapes Earth's tides. The sun shapes every orbit. And the galaxy itself gently shapes the farthest comets in the Oort cloud. A solar system is not isolated. It is a family within a galaxy. Our sun was likely born in a stellar nursery with many other young stars. Over time, those siblings drifted away through the Milky Way, lost among billions of others. Passing stars in the early cluster may have influenced the outer solar system. The sun then continued its orbit around the galactic center, carrying its planets with it. Even now, the entire solar system moves through the Milky Way. The planets orbit the sun orbits the galaxy. The galaxy moves within a larger cosmic structure, motion within motion. Order within motion. A sleeping listener on Earth is part of this movement. Lying still, breathing quietly, one is still turning with Earth, orbiting the sun, moving with the solar system around the galaxy. Stillness is local. Cosmically, there is only graceful motion. The solar system came to be because gravity found a way to turn drifting cloud into structure. And yet, gravity alone was not enough. If there had been no dust, there would be no rocky worlds. If there had been no heavy elements from older stars, there would be no Earth. If the disk had not rotated, there would be no flat planetary system. If the gas had vanished too quickly, Jupiter might not have formed. If Jupiter had formed differently, Mars and the asteroid belt might look different. If Earth had not suffered a giant impact, it might not have its large moon. If water-rich material had not arrived or been retained, Earth might not have oceans. The familiar sky is the result of many contingencies. The solar system is not inevitable in every detail. It is the outcome of natural law and historical accident. A snowflake follows physics, but no two snowflakes are the same. So it is with planetary systems. We now know that other stars have planets. Many planetary systems are unlike ours. Some have giant planets close to their stars. Some have compact systems of rocky worlds. Some have planets in resonant chains. Some have super-Earths, a kind of planet absent from our solar system. Some planets orbit two stars. Some wander freely without any star at all. Our solar system is one expression of planet formation, not the only expression, but it is our home. And because it is close, we can study its story in extraordinary detail. Meteorites fall to Earth carrying ancient minerals. Some contain calcium, aluminum-rich inclusions, among the oldest solids known from the solar system, dating to about 4.567 billion years ago. These tiny mineral fragments are timestamps from the dawn of planet formation. Chondrules, small, once molten droplets inside primitive meteorites, reveal heating events in the solar nebula. Iron meteorites may be fragments of the cores of early differentiated planetesimals, small bodies that melted, separated into metal and rock, and were later shattered. Carbonaceous chondrites contain water-bearing minerals and organic compounds, linking asteroids to the chemistry of early Earth. Every meteorite is a messenger, a piece of the beginning small enough to hold in a hand. The planets tell the story too. Mercury tells of heat and density. Venus tells of atmosphere and runaway greenhouse warming. Earth tells of oceans, tectonics, and life. Mars tells of lost water and a smaller planet's cooling. Jupiter tells of giant formation and gravitational power. Saturn tells of rings, moons, and icy complexity. Uranus tells of ancient collisions and tilted motion. Neptune tells of migration, capture, and the outer dark. The moons speak in their own voices. The moon speaks through rock, returned by Apollo, and through craters preserved in silence. Europa speaks through cracks in ice. Io speaks through volcanoes. Titan speaks through methane rivers. Enceladus speaks through plumes. Triton speaks through its backward orbit. Ceres speaks through minerals and bright deposits. Pluto speaks through mountains of ice, nitrogen plains, and a heart-shaped basin revealed by new horizons. The farther we look, the more the solar system becomes a collection of worlds, not points of light. Each world has a geology, a climate perhaps, a history, a beginning. Even small bodies have stories. An asteroid may be a rubble pile, loosely gathered fragments from an older collision. A comet may lose material each time it nears the sun, becoming darker, smaller, and weaker with every passage. A ring particle around Saturn may have once been part of a moon, then part of a ring, and may one day fall into the planet. A grain of dust may drift between worlds, lit faintly by sunlight, contributing to the zodiacal glow. The solar system is full of transformations. Creation did not happen once and then stop. The original act of formation created the stage, but the performance continues. Tides reshape moons. Volcanoes renew surfaces. Impacts open craters. Atmospheres escape. Ices sublimate. Rings spread. Orbits shift. The sun brightens. And every world responds in its own way. To make the story gentle, imagine the solar system as a garden. Not a green garden, but a garden of gravity. At the center is the sun, the great source of light. Near it, the rocky worlds are like small stones, warmed by fire. Beyond them, the giants are deep wells of gas, surrounded by families of moons. Beyond them, the icy fields remain, cold and ancient. And far beyond, in the dim outskirts, the Oort cloud surrounds everything like a nearly invisible frost. In this garden, not every seed becomes a tree. Some seeds become worlds, some become moons, some remain stones. Some are thrown away, some fall into the sun, some are preserved for billions of years. The solar system is made from both success and leftover. Planets are the successful accumulations. Asteroids and comets are the unfinished memories. Moons are children of planets, of impacts, of capture, of disks within disks. Rings are temporary ornaments, delicate and bright. Nothing is wasted in the story. Even fragments matter. For without fragments, there would be no record. The early solar system itself has vanished. The gas disk is gone. The collisions are long past. The young sun has matured. But the leftovers remain, and from them we reconstruct the beginning. Science does not watch the birth directly. It reads evidence, meteorites, crater counts, orbital patterns, planet compositions, moon systems, isotopes, computer simulations, observations of young stars elsewhere with disks around them. In distant stellar nurseries, we can see other solar systems being born. Telescopes reveal protoplanetary disks around young stars, some with gaps, rings, and spirals that may be carved by forming planets. These distant disks are mirrors of our own past. We cannot travel back 4.6 billion years, but we can look across the galaxy and see similar processes happening now. The Milky Way is full of beginnings. Somewhere, dust is gathering. Somewhere, a star is igniting. Somewhere, pebbles are colliding. Somewhere, a moon is forming around a young giant planet. Somewhere, a future ocean world may be assembling in silence. Our solar system's birth was not unique in its broad pattern. But every system has its own history. Our story produced Earth. That makes it precious to us. Now let the mind drift back again to the solar nebula. See it as it might have been. A young sun glowing at the center. A disk stretching outward, thin but immense. Inside the disk, warm regions close in, cold regions far away. Dust grains turning, pebbles forming. Planetesimals colliding. Bright shocks, silent impacts, the first protoplanets growing. Jupiter gathering gas. Saturn forming in the outer cold. Ice and rock assembling around giant planets into moons. Earth growing through collision. The moon born in fire. The sun clearing the last gas. Debris scattering outward. Comets sleeping in the dark. It is violent when described quickly. But spread across millions of years, it becomes almost calm. The violence is slow. The collisions are separated by long ages. The disk turns again and again. Orbits repeat. Gravity works without hurry. A world may take millions of years to grow. A moon may cool for tens or hundreds of millions more. A surface may be reshaped over billions. Cosmic creation is patient. This patience is important for sleep. The solar system was not assembled in a flash. It emerged, like frost forming on glass, like coral growing in a reef, like a forest rising from seeds. Only here the seeds were dust and ice, and the forest was made of planets. The first light of the sun did not rise over Earth because Earth was not yet ready. There was no horizon, no atmosphere like ours, no observer. The sun shone on molten rock, dust, gas, and debris. Later, when Earth cooled, when water gathered, when the atmosphere changed, when the surface became stable enough, then sunlight could become sunrise. The first sunrise over an ocean must have been wordless. No eyes to see it, no birds, no trees. Only light, water, cloud, stone, and the moon, perhaps much larger in the sky. The solar system had produced a scene of extraordinary calm after unimaginable formation. Earth, under the young sun. The moon overhead. Impacts still occasional, volcanoes active, oceans forming. Chemistry unfolding. In the far distance, Jupiter moved as a bright point, Saturn fainter, Mars red, Venus brilliant, all of them siblings of the same disk, all born from the same cloud. One of the most beautiful truths in astronomy is that the planets are related. They are not strangers placed around the sun by chance. They formed together. They share an origin. They are different because they formed in different places, grew to different sizes, gathered different materials, suffered different impacts, and evolved under different conditions. Mercury is not like Neptune, but both came from the solar nebula. Earth is not like Jupiter, but both orbit the same star because they formed from the same rotating disk. The moon is not like Titan, but both reveal how smaller worlds gather around larger ones. A comet from the Oort cloud and a basalt rock from Earth both trace their ancestry to that ancient cloud. The solar system is a family with a common past, a family of rock, gas, ice, metal, dust, and light. And like many families, it is shaped by both closeness and distance. Close to the sun, heat stripped away ice and gas. Farther away, cold preserved them. Close to giant planets, tides created energy. Far from the sun, darkness preserved ancient surfaces. Near Earth, the moon-shaped tides and perhaps stabilized climate. Near Jupiter, moons were pulled and warmed. Near Saturn, rings were sculpted by gravity. Near Neptune, the outer belt was disturbed. Every location tells a different story. The distance from the sun is not merely a measurement, it is a destiny. Mercury's destiny was heat and exposure. Venus's destiny was atmosphere and greenhouse heat. Earth's destiny was water and life. Mars's destiny was partial promise and loss. Jupiter's destiny was magnitude. Saturn's destiny was rings and moons. Uranus's destiny was tilt and cold. Neptune's destiny was wind and boundary. And beyond them, Pluto and its kin became icy memories. But destiny here does not mean magic. It means physics unfolding through place and time. Temperature, mass, composition, orbit, impact, history, magnetic fields, atmospheric escape, tidal heating, solar radiation. All these shape a world. The birth of the solar system set the initial conditions. The next 4.6 billion years wrote the details. Consider the sun, still shining at the center. It contains more than 99% of the solar system's mass. The planets, moons, asteroids, and comets are only the remaining fraction, the leftover disk material that did not fall into the star. And yet, from that small remnant came astonishing variety. A blue world, a red world, a ringed world, a volcanic moon, an ocean beneath ice, a methane sky, a comet tail, a dwarf planet with mountains of frozen water. The sun is dominant, but the leftovers are rich. This is another gentle lesson from the solar system. Great things can come from remnants. The planets are, in a sense, what the sun did not take. They are the dust that remained, and in that remaining dust, complexity grew. Our own existence belongs to the leftover matter of star formation. We are not at the center by mass. We are not the largest. We are not the oldest. We are a late expression of a small fraction of a disk. Yet we can look back and understand. The solar system, in producing Earth, eventually produced minds capable of asking how it formed. This gives the story a circular beauty. The cloud collapsed. The sun formed. Earth grew. Life arose. Consciousness appeared. And consciousness now reconstructs the cloud. The solar system remembers itself through us. Let the narration slow now and move outward one last time. From Earth, look inward. Toward Venus, bright beneath clouds. Toward Mercury, close to the sun, crossing light and shadow. Look outward. Toward Mars, cold and dusty. Toward the asteroid belt, where unfinished worlds circle. Toward Jupiter, enormous and banded, with storms older than human memory. Toward its moons, 4 bright jewels first seen by Galileo through a small telescope. Toward Saturn, pale gold surrounded by rings so thin they would vanish edge on. Toward Titan, under orange haze. Toward Enceladus, breathing ice into space. Toward Uranus, tilted in blue-green quiet. Toward Neptune, distant and deep. Toward Triton, captured and frozen. Toward Pluto, Charon and the Kuiper belt. Toward the scattered disk. Toward the Oort cloud, so distant that the sun is only a bright star. And then farther still, out into the galaxy. There, the sun becomes one star among hundreds of billions. The solar system becomes a tiny moving island of order, a family of worlds born from dust, carried through the Milky Way. For 4.6 billion years, it has endured. It has changed, but it has endured. The planets remain in their courses. The moons continue their dances. The sun continues its fusion. Comets still sleep in the cold. Asteroids still circle in the belt. The moon still raises tides on Earth. And Earth still turns, carrying night across oceans and continents. The story of how the solar system came to be is therefore not just a story of the past. It is the story beneath every present moment. Every sunrise is the light of a star born from a collapsing cloud. Every tide is the pull of a moon born from impact. Every mountain is made from elements forged in ancient stars and gathered into Earth. Every meteor is a tiny leftover entering the atmosphere. Every planet in the night sky is a sibling from the same disk. Every comet is a messenger from the cold outskirts. Every breath is taken on a world shaped by cosmic formation. The solar system is not remote. It is here. It is beneath the feet. It is above the head. It is in the body. The calcium in bones, the iron in blood, the oxygen in lungs, the water in cells, all trace back through Earth, through planetesimals, through dust grains, through older stars, through the galaxy's long memory. To fall asleep under the night sky, even unseen behind clouds, is to rest inside the outcome of a cosmic birth, a birth that began in darkness, a cloud that collapsed, a star that awakened, a disk that turned, dust that gathered, worlds that formed, moons that rose, rings that shone, comets that wandered, and one small planet where, after billions of years, the universe learned to tell its own story. The solar system came to be slowly, quietly, despite its violence, patiently, despite its fire. It was shaped by gravity, warmed by a newborn sun, sculpted by collisions, sorted by temperature, rearranged by giant planets, enriched by ancient stars, and softened here on Earth by water and time. And now it moves onward. The sun will continue to shine for billions of years more. The planets will continue their long orbits. The moon will continue to drift slowly away. Comets will continue to fall from the outskirts. Rings will change. Moons will evolve. The solar system is not finished, but its beginning remains written everywhere, in craters, in meteorites, in orbital paths, in ancient rocks, in the chemistry of oceans, in the ice of distant worlds, in the quiet glow of the sun. And as night deepens, the whole system turns together through the galaxy. The sun and its planets, the moons and their rings, the asteroids and comets, the dust and ice, all of it moving through darkness, all of it born from a cloud, all of it held still by gravity. A family of worlds, created from the remains of stars circling one star of their own. And on one of those worlds, beneath a calm night, a listener drifts slowly towards sleep, carried by Earth's rotation, held by gravity, warmed by sunlight stored in memory, and surrounded by the ancient, patient architecture of the solar system.